All right. It's here. It's time. Analysis Wednesday, Chapter 2, some of the solutions. I haven't done them all. Something, watch the primer material if you haven't already. It's up there somewhere. We have Anaka here. Say hello.
Hello, I'm Anaka, returning guest.
And he's going to be my guinea pig / torture victim for today. So, Anaka, do you remember the definition of power set of a set?
Yeah. Well, not the definition, but I could give you the power set. Possibly. I could try.
Okay.
So, an element would be A, and then there's element B, there's element C, and then there's element AB, there's element BC, and AC, and ABC. And if I believe that's correct, I think that's all of them.
There is one more.
Oh, the null set.
Beautiful. The way I did this before I erased it, and you said, "Oh my gosh, there's a comp sci question," was I wrote it down like this, as hopefully a more illustrative example of why the answer to part B is the way it is. Do you see possibly why I might have chosen to write this way?
Determine a formula for power set of A. Remind me on the notation of the bars again.
So this means cardinality of.
Okay.
You know, the whole thing we did last time about cardinality.
Give me a hot minute to think here.
Okay.
To the timer.
Okay,
Editing,
timer.
Rob.
Think timer. Editor, put up the think timer. Also put up a skip here to skip the thinking, but then don't actually go back and add in the time. So just have a skip to this part, but without the actual time code. Let's say I want to collect every binary number smaller than n. Or let's do a real example. Let's do like 3. Why not? Because 3 is great. So what do I start with? 0, 0, 0 seems reasonable enough. 1 seems like a pretty obvious next choice. And why not just keep going in this manner till I have all of them?
That makes sense to me.
Okay.
So you can have each element of the power set be represented by one of these binary strings, and therefore the formula that you were asking about would be 2 to the power of the cardinality of A. I think that makes sense.
Epic. So we're going to propose if cardinality of A equals n, then the cardinality of the power set of A equals 2 to the n. And we can see this is in fact right. Let's do a little parallel A, B, C. So we can have none of them. We can have just C. We can have, just B, etc. We can have all of them. This is why I originally wrote down this like this. It's the red pen, not the laser pointer. Originally why I wrote it down like this, because I viewed it as all zeros, 0, 0, 1, yada, yada. You did it another equally valid systematic way, which is just all the elements that have 1 thing in them, 2 things, 3 things, and then 0 things. There's only one of those. And we will in fact see that this is just true. That's how it is. We make a binary choice for 3 elements. We have 2 options n times, and that means 2 to the n possible combinations. Next question. 2.2. Prove that the cardinality of the cardinality of the set containing e to the n such that n is a natural number is equal to the cardinality of the natural numbers.
Is this a question for me to solve?
Do you want to solve it?
I'd like to take a crack at it.
Okay.
I probably won't get there, but I'd like to provide insights.
All right. Proof.
So just thinking about this logically, make sure I understand the question. If the elements in the set are E,
I'll write it out.
So it would be it'd be E to the power of 1, E to the power of 2, up until infinity.
Yes.
So if we remember back to last week, the cardinality of n, the cardinality of the real numbers is countably infinite, correct?
That is untrue. Cardinality of the real numbers is in fact uncountably infinite.
Or the natural numbers.
The cardinality of the natural numbers is in fact countable. That is correct.
So this is effectively asking us to prove that the set containing e to the natural numbers is countably infinite set.
Yeah.
And I would surmise that we do this by finding a bijection.
That sounds like a wonderful idea.
That's about as far as I'm getting. I don't remember how exactly to do that.
If I were to ask instead that the even numbers were as big as the natural numbers by bijecting them, how'd you go about it? You remember Hilbert's Hotel?
Yeah, every instant of rooms would go to their second room, doubling the infinite amount of spaces by going to each room would go to 2n. In this case, it's room number.
So the bijection might be the shorthand for this bad boy is just 2n. So would you agree? Every natural number goes to double itself?
Yep.
Okay. Now what if I just did this?
And then replaced the e in both of those as well. Doesn't look as pretty.
It doesn't, but it's because I refused to erase. And
it just works.
What is so different about this?
Well, multiplication is different than this is. It functions differently. So if you have 2n, that is effectively n plus n.
Sure.
Whereas e to the n is e plus e n times. I'm not sure if that is exactly expressed correctly, but I'm sure it is understandable.
E to the n is e times e, n times. That makes sense.
I suppose I can't find an exact reason why my brain doesn't like that.
Well then, let's beat your brain into submission. What do we need to show that f is bijective?
It is 1-to-1 and on-to.
All right. What would you like to start with?
Let's start with on-to.
Okay. So the way we're going to prove this is we're going to take a arbitrary element of this set, and we're going to say that something in the domain maps to this.
So something maps to, so the element of e to the power of n is our output set, right? Yeah. In this example,
a is in the output space. We want to find something in the input space that maps to it. What do we know about every element of e to the blackboard n?
Every element is a power of e.
Okay. There is some natural number such that a equals e to the n. Do you agree?
I believe that is the only thing we know about it.
Okay. F of n. What is f of n?
F of n is equal to e to the power of n.
So we found something in the domain that maps to this, haven't we? It's n.
Yes.
Okay. F is 1-to-1. What do we need to prove?
That only one thing maps to each of them, each output.
Okay. How do you want to do that?
My intuitive logic tells me that for any e that is not 0, it makes sense. However, I don't have the proof skills in my back pocket to think of a way to prove it.
Okay. So what we want to prove is that I'm going to write this down formally. So if two inputs give the same output, then those two inputs have to be equal to each other, which means there do not exist two distinct inputs which give the same output.
Okay.
So there are even two ways to do this. We can either assume some f of x1 equals f of x2, show x1 equals x2, or assume some x1 is not equal to x2 in the domain, show that f of x1 is not equal to f of x2. What would you like to try?
I would like to try the second one.
I think I would like to try it that way too. That seems easier to me. Okay. So let's call them n1 and n2 be in the domain, which is the naturals, recall, with n1 is not equal to n2. All right, what next?
We have to show that the output of the function of each of those are not equal to each other.
Okay. We're going to do this in a way that does work. Assume Wolog that n1 is bigger. Wolog means without loss of generality, because by trichotomy of R, which n is a subset of R, so this also applies to n, if two things are natural numbers, then one of them is smaller than the other, they're equal, or that one is bigger than the other one. And so I could go, there are two cases, n1 is the bigger one, or n2 is the bigger one, but it doesn't matter because they're arbitrarily chosen with the exact same constraint. So I can say without loss of generality that n1 is the bigger one. Sense make?
That makes sense.
Okay. What do we know about f of n1? This is equal to e to the n1. Similarly, f of n2 is going to be equal to e to the n2. And then by a greater than b implies a to the n bigger than b to the n, e to the n1 is greater than e to the n2. Implies f of n1 bigger than f of n2 implies f of n1 not equal to f of n2. Does that look good to you?
Do we not have to assume that, or state as a premise that e is not 0?
It's...
Or is e a constant that I am not aware of?
E is approximately 2.71182818459045, and then some other stuff. But it is bigger than 0.
Okay. Well, that is... I now agree and understand, and this makes sense.
So anytime there's an e, it's not some random variable, it's this. Like how anytime you see a pi, you know what that is?
Yep.
It's the same thing for e, unless you're in algebra or like group theory where they use e as the identity. I don't know why. Great. So if I have everything right, that means we've just done it. F is bijective. And that's it.
That makes sense to me.
Moving on. Write down an explicit bijection between each pair, between 0 infinity and 1 infinity. And these are intervals. They are subsets of the real line. Are you familiar with this notation?
Yes.
You want to take a stab at letter A?
Yes. Remind me about the notation. The curved brackets are exclusive or inclusive?
That means do not include the endpoints. So
Okay,
0
so
is not
exclusive
in the set on the left. It'd be weird if this interval included infinity.
Okay, so it's asking me to write down an explicit bijection.
Mm-hmm.
What exactly is that asking for?
A function between the two sets that is bijective.
I guess can we give the first set a variable name?
Let's
Is that a legal action?
Let's just say it's from 0 infinity to 1 infinity.
So f of x is equal to x plus 1.
The question, in fact, says you do not need to prove your answers. Phenomenal. This just works. I'll tell you that. Now what about this one?
F of x is equal to negative x plus 3.
That's what I have in my notes over here.
Okay. Ooh, this next one looks a bit more tricky.
0 infinity and 0 1. That does look tough. What are your thoughts? I have a bunch of space down here for graph drawing.
I feel like it is f of x equal to 1 over... Wait.
Let me draw you a graph.
Yeah.
This is what negative 1 over x looks like. on the right side.
Okay, so it would be -1/x plus 1.
Okay. So that's going to look something like this. This is x equals 1. So all these values between 0 and 1 don't get mapped to something between 0 and 1 here. This is an easy fix. We're just going to move it. -1/x. We shifted it to the left. You could try this. Plug in 0 here, and it'll get you 0. Then anything bigger makes this denominator bigger, which makes this number closer to 0, which makes this whole thing closer to 1. There you go. Okay, between r and 0 infinity.
So the set R, which is the real numbers.
Yep. So if we draw another picture, we want something that covers the entirety of 0 to infinity. Somehow. A function that looks like this would do the trick. E to the x works. R and 0, 1. Now this one's pretty unstandard. So I'll just give it to you. F of x, it's in my notes here, equals tan pi x plus a half. And that's going to look 0, 1. That's going to look like this. Oh my gosh. I have spoilers. Oh, well, it's fine. Between the integers and every integer power of 2, this is exactly the same as what we had to do in 2.2. We just map each element of this to the corresponding power, which made it that way. 0, 1, this is the set containing 0 and 1. 0, 1 cross n and n.
Set multiplication is not something...
This is not set multiplication. This is the Cartesian product. So 0, 1 cross n looks like this. It's the set all ordered pairs A and B with A in 0, 1, B in n. So stuff like 1, 5, 0, 10, not 0. Yes, 0. 0, 1, 1, 1, anything that looks like that.
Okay. I understand. And logically, I understand that that is effectively 2n. Does that make sense?
Yeah. It should be in our puny human brains. That should just be twice as many things as n, which should be countable. So what do you think? I'm going up to Hilbert's Hotel, and I've got me and my infinitely long marching band. How do we all fit?
Well, you just send everyone that is currently in the hotel to twice their room number, and then fill in the infinitely created new spaces with your infinite marching band.
Great. So what's the bijection?
F of x is equal to 2x.
Our input space is a set of ordered pairs.
So f of...
Let's call them A, N. What happens to this ordered pair?
I am not sure I am following.
So the infinitely many me's should go into the even rooms, and my infinitely long marching band should go into the odd rooms. So how about I give my infinitely long marching band, I give them each a 1 as a sticker. I stick a sticker on their head. It says, you are assigned to 1. And then the infinitely many me's, I assign a 0. So the infinitely many me's could go to the even rooms, and then everyone in my marching band should go to an odd room.
Okay.
So if I'm a me, let's say I'm a 0, 5. I will go to 2 times 5 minus 0. So I'll go to 10. If I'm a 1, 5, I'll go to 9.
I see. That now is clear to me.
Okay. The closed interval from 0 to 1 and the open interval from 0 to 1. When we had intervals before, we thought about graphs and we thought about continuous functions from this interval to that interval. Topology tells us there are no continuous bijections between these two sets. So we've got to be a little crafty, as the subtitles say. So I'm going into Hilbert's Hotel. Actually, I can't use Hilbert's Hotel here because that's countably many rooms. So I show up to the open interval 0, 1, and I am the number 0, and I bring my friend 1. We can fit in here, and it's by telling a subset of everyone in the interval hotel to move down, but most of them go undisturbed. We're going to map most of the continuum to itself and shift some sequence of reals, like in Hilbert's Hotel. Which to choose? Who knows? Let's define a set A to be the harmonic sequence. That's everything that looks like 1 over n, with n being a natural number. So if we have 0, 1, whoa, why'd that make an arrow? That's crazy. Anyway, we have 1/2 is in here, 1/3 is in here, 1/4 is in here, 1/5 is in here, 1/6 is in here, and so on.
Follow.
So what's going to happen when I try to, these are the open interval now, so I'm not filled in these circles from 0 to 1, is that I can cram in 1 and 0 if I tell the harmonic series to shift down. 1, 2, 1 over 3, 1/4, 1/5, 1/6. So if I put this guy in here and put this guy in here and tell everyone else to move down to, who goes unhoused? Nobody. Everyone else that's not in the set just gets mapped to itself. Sense make?
Sense make.
Okay.
Although I am confused why this is any different than the normal situation where you're just putting in 2 additional people and why we need the harmonic sequence.
Because we can't displace it gets funkier with uncountability. The unit interval, as we know, is uncountably infinite, so its cardinality is strictly greater than the cardinality of the naturals. So we can't just displace one person. We can't just shove 1 into the number smaller than 1, because there isn't a next number that's smaller than 1. So we find a discrete set that we can do this to, and we know this works.
Okay.
Where there is the next number in the harmonic series.
I see. Now I understand. It makes sense to me.
Then f from, what is it? 0, 1 to 0, 1. Whoops, not 2, but right arrow. By f of x equals, if something's not in A, map it to itself, and 1 over n plus 2 if there exists some n. Oh, no. All right, now I've got it. I broke myself, but I'm fixed now. It's 1/2 if x is 1, 1/3 if x is 0, and 1 over n plus 2 if x equals 1 over n. Let's say for some. That's better. Okay. For this problem only, define a relation on sets tilde by A is related to B if and only if there's a bijection from A to B. Show that tilde is an equivalence relation. I'm going to assume you don't know what that means.
I would like a further explanation.
Okay. A relation, it's a way to compare two objects. Maybe that's better. So frequently, less than or equals is used as an example of a relation.
Okay.
1 is less than or equal to 2. It's a way of comparing two things.
Okay, so an equivalence relationship is just the equal comparator.
So, well, an equivalence relation is a special type of relation that has a few properties that we like. So we generalize stuff like less than or equals, greater than, stuff like that. And now we're thinking about just relations, comparing two objects. An equivalence relation has the following properties, and we use tilde for a general relation. Tilde has to be reflexive. That means any element is related to itself. It has to be symmetric, meaning that if A is related to B, then B is related to A. And it has to be transitive, meaning if A is related to B and B is related to C, then A is related to C. So we can actually see for less than or equals, some of these hold. A less than or equal to A, that's true.
Mm-hmm.
A less than or equal to B implies B less than or equal to A is not true. Counterexample, 1 is less than or equal to 2, but 2 is greater than 1. And it is transitive. So 1 less than or equal to 2, less than or equal to 3, and 1 is indeed less than or equal to 3. So let's check this equivalence relation being equine numerosity, there being a bijection between two sets. Let's check that for these properties. So I want that A is related to itself. That means I need to show there's a bijection between A and itself. How do you think I should find a bijection from A to itself?
F of x is equal to x.
That sounds like a phenomenal idea to me.
Genius.
Okay. Symmetry. A is related to B implies B is related to A. So, given there exists some function from A to B that is bijective, known F inverse exists and is bijective. That is part of being a bijection, is that means a function is bijective if and only if, in fact, it has a well-defined inverse.
Yeah, because otherwise it couldn't be one-to-one and onto.
Okay, transitivity. So we are now to assume that my pen's eventually going to start working. So given there exists F from A to B and G from B to C that are both bijective, how show A related to C? Well, one thing we know is that by composition of bijections is bijective. Doing G composed with F from A to C is bijective. Done. Pretty simple one.
Can you explain what by composition of bijections
So
is bijective means?
Composition of functions is doing one function and then doing the other one. So G composed with F means we take some input, we do F to it, and then we do G to that.
Okay. That is a notation I'm more familiar with. I understand now.
Next one. If A and B are countable, then so is A union B.
So my brain is thinking about some things.
Okay.
And
You want to let me in on some of them?
yeah. So if A and B are countable, at least if we're thinking back to Hilbert's Hotel, you can have a countable countably infinite amount of rooms, and then you can just have everyone move to the twice their room number, and then you have countably more infinite. So the union of A and B is, if I'm not mistaken, just kind of like putting A in all the even rooms and B in all the odd rooms. Does that logically track?
Ignore this. This is useless garbage. I called them A1 and A2 instead of A and B because all right.
Okay.
So there's some F1 from A1 to N and some F2 from A2 to N. And F1 and F2 are both injective.
Mm-hmm.
Okay.
So F1 and F2 are functions?
Yes.
Okay.
Anytime you see this symbol, colon, set, right arrow, set, that means the thing is a function. We're going to get funny. So we're going to define phi from A1 union A2 to N cross N by phi of A equals N, comma, Fn of A, where N is the smallest element of the set containing 1 and 2, such that A is in big A N.
What does it mean by N is the smallest element of the set of 1 and 2, such that?
So if A is in A2, then N is 2. Apologies. If A is in A2, then N is 2. If A is in A1, then N is 1. If A is in A1 and A2, then N is 1.
Okay.
We're going to show that phi is injective. That means we're going to suppose that some two outputs are the same. Phi of x1 is equal to phi of x2. How is phi defined? Well, it's right here. N Fn x1 equals N Fn x2, which means that N equals N, because these things are equal. Both of these things have to be equal to each other, and these two things also have to be equal to each other. So Fn x1 equals Fn x2. Since Fn is injective for n equals 1 and 2, that means x1 equals x2. That's the definition of injective.
This makes sense.
Okay. And we're actually done. We can put a box there. Bicountable cross countable is countable. There's an injection G from n cross n to n. And by composition of injections is injective. G composed with phi from A1 union A2 to n is injective. Countable cross countable is countable. We're going to prove that later for exercise 2.9. Sound good?
Sounds good.
All right. Now, prove that if we have a collection of sets. AN is a countable set for every natural number n. Then the union of all of those sets is countable. The union of two countable sets is countable. So this seems like a job for induction. So if A1 and A2 are countable, then A1 union A2 is countable by part A. Done. That's the base case. For the inductive step, we suppose that the union up to K is countable by A, since the union up to K and AK plus 1 are countable, then the union of those two sets is countable. So therefore, by induction, the union of all of the sets is countable. Does this sense make?
I'm thinking that this makes sense.
Wonderful. Awesome. Seems I have left my answer up for this one. Show that the cardinality of n equals the cardinality of z by finding a bijection. So we say, oh no, I've rocked up to Hilbert's hotel, but I have my friend Gallantry and also my infinitely long marching band of negative numbers. But we know this doesn't matter. So if n, I just send all of the odd numbers to a non-positive integer, and then all the even numbers go to half their number. So if n is odd, then send it to a negative integer. Otherwise, send a number to half of itself. And
This makes sense.
for 0, for 1, I guess, this comes out to 0. 1 goes to 0. 2 goes to 1. 3 goes to -1. And you can see how this would alternate. 4 goes to half of itself. 5 then goes to -2. And so on. One of these parts, I in fact do not have an answer for, which, we'll get to it. So let A and B be subsets of real numbers. Give some examples of the following things. And A and a B such that the cardinality of the product of A and B is less than the maximum of the cardinalities of A and B. So maximum just means whichever one of these is bigger, that's what this returns.
Incredible. Then we're supposed to give examples.
Yeah, I have my examples written over here. So if A equals 0 and B equals just 1 and 2, then A times B is just going to be 0, ain't it? Because the elements are going to be 0 times 1 and 0 times 2, which are both 0.
Yep.
The cardinality of that set's going to be 1. But cardinality of B is 2, so this is at least 2. Phenomenal. And A and a B such that cardinality of A times B is greater than the max.
That makes sense.
For this, I just chose some prime numbers. Made sense enough.
It's going to be, 10, 14, 15, and, oh God, mental math. It's not
21.
strong with me. 21.
Yeah, so the cardinality of this is going to be 4, but this is going to return 2. And then, of course, A times B is equal to max. That's easy as pie. Just both of them 1.
Yep.
I mean, they could be any 2 singleton sets. It don't matter. Okay. For which of the above does there exist an example where one or both of these sets is infinite? So for A, if we still have A equals 0 and B is the real numbers, for example, then the cardinality of A times B is still just going to be the cardinality of the singleton set containing only 0. And that's going to be less than the max of both of these cardinalities, because that number is going to be at least the cardinality of R. If we know, in fact, it's bigger than 0 or bigger than 1. And for B, I couldn't think of an example of an A and a B such that the cardinality of A times B is greater than the max of cardinality A, cardinality B.
To the above. Well, A times B is greater than... Yeah, it's hard to multiply something by something that's infinite and get something that's uncountably infinite as far as my understanding goes. So I'm going to agree with you. So that's like the main issue, right?
Yeah, I couldn't
You need to get something from infinite to
I don't think
uncountably infinite.
I don't think something like this exists. Of course, I am but a lowly bachelor's degree. I could not prove that such an A and B can't exist. So
Yes, in the comments.
Yeah, PhD students in the comments. And for C, in fact, if A and B, if they're both n, then n times n, the cardinality of n times n, is equal to the cardinality of n, because it's countable.
Yep, that one is pretty easy.
You could also do A is 1 and B is n. 2.9. What happened to 2.8? It's gone. All right, editing Rob, you know what to do. Speed up the part where I write down the question. Okay, we have 2 questions here. Describe a way to partition n into 6 subsets, each containing infinitely many elements.
Okay, n is the natural numbers. Okay, positive integers. 6 subsets. Can the subsets overlap?
Partition is a way of divvying up a set such that each subset. So no, two parts of a partition cannot overlap, and also the partition must contain the entire set.
The partition. Explain what you mean by the partition.
So let's draw a circle.
Yep.
I'm going to partition this circle.
Mm-hmm.
Call each of these a subset of the circle.
Okay. And these are partitions.
This
so
is a partition.
6 partitions.
Each of these, none of these overlap with each other. And their union is the whole circle. It's supposed to be a circle.
I think I can do this.
Oh, yeah? All right, give it to me. What do you think?
Can I call one of the partitions everything else? Is that a legal statement?
Yeah. That all of the subsets have to contain infinitely many elements.
Okay.
Keep that in mind.
We can call one partition divisible by 2.
Okay.
Sure, there's a better way to write that out. Okay. One of them call divisible by 3.
Where does 6 go?
Okay, true. I was going to think about prime numbers, but maybe I didn't think about it backwards. Seems like quite an interesting thing that I feel like I can do.
I feel like you can do this too.
Might require a thinking timer and a fast forward.
My dear computer scientist, I believe in you.
And okay, yeah, they can. Okay, never mind. Answer my own question. It's a good question.
What you thinking about?
A strategy for partitioning natural numbers is what I'm thinking about.
Okay. Think out loud to me. Let me hear your thoughts.
So, of course, the first thing that I thought of is you could partition them into being divisible by prime numbers, but obviously that doesn't work because non-primes are divisible by multiple prime numbers.
Tell me a story about modular arithmetic.
I'm not familiar with this story, or at least not by that name.
You know about modulo?
I am
it's a
familiar
function.
with modulo.
Function in many languages. It returns the remainder of a number after being divided by the number on the right.
Yep, I am familiar with this as a computer scientist.
Okay, I was hoping you would be.
That would be wild if I wasn't.
How many possibilities are there if I take a natural number modulo 6?
There are 6. 0, 1, 2, 3, 4, and 5. Those seem like 6 infinite and distinct subsets to me. That seems like a valid answer.
Where this denotes the equivalency class of x under modulo 6. What that means is this is 0, 6, 12, 18, 24, etc. This is 1, 7, 13, 19, 25, and so on. This is multiples of 6. This is multiples of 6 plus 1, plus 2, 3, 4, and 5.
Okay.
B. Describe a way to partition n into infinitely many subsets, each containing infinitely many elements.
Well, I don't think we can use the previous strategy, or at least not directly.
How come?
Can you modulo infinity something?
Yeah, that would be hard, wouldn't it?
And them not come out to be like 0 modulo infinity come to 0 and 1 modulo infinity come out to 1.
Yeah, that would be.
And then they'd be singular elements.
That would be rough. So let's not do that. What are some things we know about powers of primes? And what are some things we know about primes?
Well, primes cannot be divided by anything except for themselves and 1 and get an integer number.
All right. What are some things we know about powers of primes? that are positive powers, so not 0.
Powers of primes.
How many powers of 2 are there?
Infinite.
What about 3?
There are infinite powers of 3.
Does 2 divide any powers of 3?
No.
Does a prime divide a power of a prime that's not itself?
Can you say that one more time?
So if P and Q are distinct primes, my question is, does there exist some natural number such that P divides Q to the n?
Such that P divides Q to the n. So that would be Q to the n over P.
That means
Evenly divides to something?
that means Q to the n over P is an integer. Is this possible?
I don't believe so.
You oughtn't, because there isn't. So we know, 1, by Euclid in approximately 500-ish BC, I think, there are infinitely many primes. Fact 2, for every prime, P, there are infinitely many powers of P. And for any distinct primes, P and Q, no power of P can divide any power of Q. And that also means no power of P can be equal to any power of Q.
I am not convinced, without further thought, that powers of each prime number make up all of n. Does that?
They don't, because what about 9? Hello? Did you forget about the composite numbers? And numbers that are not powers of primes? Here's what we're going to do. We're going to do the thing you suggested. We're going to split this into powers of primes and everything else.
Oh, incredible.
Okay. So, for each prime P, define AP to be all the powers of P. So P to the n bigger than 0. And then define B to be n in the naturals such that n is not in AP for all P. Or how about for all P, n is not in AP. Then n should be the union of all the primes AP union B. Either a natural number is a power of a prime or it's not. That's pretty great, isn't it?
Would say so.
Is cardinality of Z cross n countable or uncountable? By countable cross countable is countable. Z cross n is countable. Brilliant. Let's move on. No, I'm just kidding. Okay. The Cartesian product of countable sets is countable. So let A and B be countable sets. We discovered something during the primer material, and it's that if something's countable, then it can be listed. And B looks like this. We set up something cheeky. We know that A cross B is every ordered pair AB with A in A and B in B. So we set up something a little familiar. Do you remember this?
Yes, I remember something that looks distinctly like this, where we follow the diagonals to hit
Yeah.
all the elements.
That's it, really. This is going to hit every ordered pair.
Yep.
I am prepared to call that finished.
That I am convinced.
Great. Therefore, Z cross n is countable. Let S be the set of sequences AN, where for each n, AN is in 0, 1. Is S countable or uncountable? Do you remember the game we played where I wrote down 5 sequences and your job was to construct one that wasn't one of mine?
Yes, I remember figuring that one out.
And you diagonalized?
Yes.
So we can do the exact same thing. Take all these sequences of zeros and ones. We can come up with one that's not on the list. by diagonalizing. So this set is uncountable. Wonderful. Okay, it looks like we're getting to the end of my prepared solutions. Suppose that X is a non-empty set. Prove that the following are equivalent. That's what TFAE means. X is finite or countably infinite. There is an injection from X to the naturals, and there is a surjection from the naturals to the set. Surjection means onto, injection means one-to-one.
TFAE means what again?
The following are equivalent. So if any one of these is true, then so are the other two.
Okay.
And what we do here is when we're given a list, we just go 1 implies 2, 2 implies 3, and 3 implies 1.
Okay.
Okay? So 1 implies 2. X is finite. Okay? Then the cardinality of X is going to be strictly less than the cardinality of N.
Mm-hmm.
So there's an injection from X to N.
That makes sense to me.
And if X is countably infinite, then there's a bijection between the sets. That's what countably infinite means. And hence, bijections are injective. Hence, there's an injection from X to N. Okay, now for 2 implies 3. So we assume 2 and try to prove 3. If F from X to N is an injection, that means that cardinality of X is less than or equal to the cardinality of N, which means that the cardinality of N is greater than or equal to the cardinality of X. So by fact 2.4 in the book, there is a surjection G from N to X.
What is fact 2.4?
Fact 2.4, the cardinality of S is greater than or equal to the cardinality of T if and only if there is a surjection from S to T. And now for 3 implies 1. If G from N to X is a surjection, then cardinality of N is at least the cardinality of X. So the cardinality of X is at most the cardinality of N. So either cardinality of X equals the cardinality of N, which means X is countably infinite, or cardinality of X is less than the cardinality of N. So X is finite. The fact that the cardinality of N is the smallest infinity, that any set whose cardinality is strictly less than the cardinality of N is finite, is another exercise that we prove later. 2.12 is interesting. Give an example of a collection of countably many disjoint open intervals, or prove that one doesn't exist. So for this, I just took every open interval from a natural number to the next one. Mm-hmm. Those are all disjoint because they're open intervals. Yeah, this could be literally anything less than 1. This could be a 69th for all I care.
Hell yeah.
But 1's fine. Give an example of a collection of uncountably many disjoint open intervals, or prove that one does not exist. What do you think?
So the first one is give an example of a collection of
countably many disjoint open intervals, or prove one doesn't exist. Now we're asked to do the same thing, but replace countably with uncountably. In my mind, this is my musing, such a collection shouldn't exist. That's what I think. I do, in fact, prove this. What is your initial reaction? Do you think such a thing should exist, or it shouldn't?
I'm still thinking about the first one and need to comprehend that before we move on to the second one.
Okay.
So the first one, okay, so any interval between an integer is countably infinite.
So what it's asking for is a collection of countably many disjoint open intervals. We don't care about the size of the intervals. We just care that there are countably many of them. Oh,
okay. I understand.
So just countably many blue things. We don't care how big the blue things are. We could just as easily say a blue is a continuum from 1 to 2 greater. Okay. And then we only have every even number or every odd number or something is the start of an interval.
So uncountable.
So should there exist a collection of uncountably many disjoint open intervals?
Well, the only uncountable thing that you've introduced us to is the real number line, right?
Yeah, and yes, and subsets of it.
And subsets of it. So why can we not give a collection of subsets of the real number line?
They have to be disjoint, and I'll tell you why that's a problem.
Okay. Convince me. Explain it to me.
All right. Suppose that script U is a collection of disjoint open intervals in R. Just a collection of disjoint open intervals. Okay? Are you on board so far?
I'm on board.
Okay. Since blackboard Q, which is the rational numbers, is dense in the real numbers, and what that means is every two distinct real numbers has a rational number in between them. That means every UI, think of UI as an interval in the collection script U, every UI contains a rational number QI. Does that sense make?
Sense. Can you explain?
Any two real numbers has a rational between them. So any interval has to have a rational number in it.
Okay.
Does that make more sense?
Since Q, so the rational numbers are dense in the real numbers.
Yes.
So rational numbers is just, if I remember correctly,
it's any ratio between integers.
Okay. And what does the terminology dense mean?
Dense, when one set is dense in another set, in this case Q is dense in R, means pick any two distinct elements of R. There is a rational number that is strictly between them.
Okay.
All right, and that means every interval in the collection has a rational number in the interval.
Well, Q being dense in R does not make intuitive sense to me, but if you are saying it's true and I'm choosing to believe it, then the rest of it makes sense.
Okay, I will draw you a picture. We have the real number line. Just pick two numbers. Let's call them positive for now. So 0's over here. A and B, they're not equal, so one of them has to be bigger. Let's just say that B is bigger. This distance is some positive real number.
Yep.
By the Archimedean property of the real line, there is some n big enough such that 1 over n is smaller than d.
Yep.
And that means if we take multiples of 1 over n and we just keep adding on 1 over n to itself, eventually we're going to hit a, and either some m over n is going to be smaller than a, in which case m plus 1 over n is going to be in between a and b, or that m over n is going to be between a and b already.
Okay, I'm convinced.
Great. And obviously we can say that if a ended up being a multiple of 1 over n, then we can just add 1 over 2n, and that won't get to b, but it'll still be rational. So you are now convinced.
Yes.
Okay. So every UI in the collection script U contains a rational number QI. Okay?
Mm-hmm.
By the axiom of choice, we can assign every UI a unique QI. So we have a function. Let's just call it f. F goes from script U to blackboard Q, and f of UI equals QI for every element of script U.
Okay.
Then define the function the way that I just said. So f of UI equals QI if we define a function f from script U to Q by f of UI equals QI, then f is an injection. The elements of script U are disjoint So no 2 can contain the same rational number. So f is 1 to 1. And that means the cardinality of script u is at most the cardinality of q, which we know is countable. So the cardinality of script u is at most countable. So any collection of disjoint open intervals is not uncountably infinite. So there are no uncountable collections of disjoint open intervals.
This makes sense.
Wonderful. That's all my prepared answers. We just did 12. There are 22 in this chapter. So we're done now. Script snurb and hit the bell and like the comment on the subscribe bell.